Hello students. Today we will solve two problems that are asked in your sessional 2 exam. Here is the first problem. An electron is moving under the influence of potential of 50 volt. Calculate the frequency of the wave representing the electron. Okay, we know from quantum mechanics that electron can be represented as a superposition of group of waves that are having different frequency, and here we are going to find the average frequency of these waves that represent the electron when it moves under the influence of 50 volt difference. Okay, we know from the de Broglie wave particle duality that when electron has the momentum of this much, it will have the wavelength of this much. Lambda is equal to h by p, where h is the Planck's constant. Okay, so if we know the wave velocity, one can find the wave velocity by multiplying the wavelength and the frequency of the wave. Okay, now from substituting the lambda from here, equation 1 into equation number 2, one will get the velocity as nu times h by p, and p is nothing but mv momentum, and taking the mv this side of this equation, one will get mv squared as h nu. So multiplying this equation by half, one will get half mv squared as half h nu. Okay, now since electron is moving under the potential difference of by a potential difference of 50 volt, its classical non-relativistic energy half mv squared will be equal to E time, electronic charge time the potential difference V. Okay, so half mv squared is equal to EV, and substituting here EV, one can write EV as half h nu. So EV is equal to half h nu, and so rearranging this equation, one will get the frequency as 2 EV by h, and putting all the constants values, one will get the frequency as 2.415 into 10 raised to 16 hertz. So this is the answer. Here is the second problem. An electron is trapped in a rigid box of with 4 Armstrong. Find its first excited energy level and calculate the probability of finding the electron within 1 Armstrong to 4 Armstrong. So here an electron is trapped between a rigid wall of infinite potential which has the width of 4 Armstrong. So an electron is trapped between infinite potential wall between 0 to 4 Armstrong. Okay, so we have to find the probability of finding the electron within 1 Armstrong to 3 Armstrong in this interval. Basically it is half of the box. Okay, so if we think classically, what one would assume is, since electron is a particle, classically we would think that electron is a particle and it has equal chance of being found anywhere within the box. It can be here, it can be here, and it can be here. So if you ask the probability of finding the electron within this half of the box, we will tell it is half. Okay, but let's see what quantum mechanics gives. So we know from quantum mechanics that for a particle confined in an infinite potential well, the energy eigenfunction is given by this: psi n is equal to square root of 2 by a sine n pi x by a. Here a represents the width of the box. Here it is 4 Armstrong. Okay, now the energy eigenvalues are n squared, pi squared, h cut squared by 2m a squared. Okay, here h represents Planck's constant, and h cut is the reduced Planck's constant, which is h by 2 pi. Okay, now what it is asked, the energy of first excited state energy, whereas n is equal to 1 corresponds to the ground state energy, and n is equal to 2 corresponds to the first excited state energy. We should not start n is equal to 0. We have to start from n is equal to 1. So substituting for n is equal to 2, one will get this h squared by m a squared. Substituting the values of m and a, one will get the energy, second excited state energy as 0.188 into 10 raised to 2 electron volt. So 18, this is equal to 18.8 electron volt. Now let's proceed to find the probability. So from the Bohr's probabilistic interpretation, the mod psi squared, the wave function squared, mod of wave function squared gives the probability density. So if we want the probability over some region, so just multiply by the region. Okay. So here in this problem we need between the interval 1 Armstrong to 4 Armstrong. So integration from 1 Armstrong to 4 Armstrong of this quantity will give the total probability over this region. Okay. Now doing the integration, one will get this. So square root will go when we take mod square. It is 2 by a and sine squared by x. We know sine squared as 1 minus cos 2x by 2. Invoking that formula and taking out the constant will give you this term. And so breaking the bracket and doing the integration, one will get this equation, and substituting the lower and upper limit, one will get this 3 Armstrong by 1 Armstrong by 4 Armstrong. Here A is 4 Armstrong, and this 3 Armstrong by 4 Armstrong. So Armstrong we can get, so it can be written as 3 by 4. Armstrong by Armstrong can be cancelled. It is 1 into 10 raised to minus 10, and so 1 by 4 cancelling this, so one will get this sine 3 pi by 2. Sine pi by 2 we know sine 3 pi by 2 is minus 1, and here sine already one minus sign is there, so it will give 1 by 2 plus pi 1 by pi. So this is more than half. You can see it is more than half. Classical result should give half, but quantum results gives me the probability as 0.818. So it is more than 3 by 4 actually. So that's all. Thank you.